I have to give it some little pressure.
Okay, good morning. Oh, I'm not projecting. Share. Um, and it could be on screen settings. Right, so restart. It's connected. Sorry for the delay. Um, so yes, good morning again. Hey, we passed homework one, and I want to a little bit reflect and ask you why there was this weird neighborhoods. Because if we take the neighborhood of this point, the circle, it should be a circle, but why it's actually not a circle, but this polygon. Any guesses? Which metric did we use? Yeah, you could just pick.
Yeah, I'm just gonna, guessing that the little blip is the result of the Manhattan distance and how that's computed because in the when I worked with the homework, I used the Euclidean distance by mistake like one time.
Mm.
And it was in fact like more like triangle-ish kind of thing.
Mhm. That's right. So if we look at this point, for example, oh, wait a second, what's happened? uh, I want to annotate. So if you look at this point, for example, and consider the circle in Manhattan distance, it will look maybe like this. So that's why the neighbor will be a blue square. Does make sense? Okay. So the second comment, let's clear all drawings. The second comment on this um, pitch detection. Last time we talked about binarization. So if we binarize our data, then the pitch detection will work perfectly without any models. We just split into bins our data into how many bits here? 1, 2, 3, 4, 5, I believe. So sometimes you don't need to use any complicated algorithms or models. You can just binarize your data and get nice result. Just assign each node to the range of frequencies and you're done. So let's talk about pros and cons of k-nearest neighbors. Let's see if I have it here. I should have them somewhere. Okay, so k-nearest neighbors. The algorithm is very simple. So it has just few hyperparameters, the number of neighbors, the distance formula, maybe metric. And there are some problems where k-nearest neighbors works actually better than other algorithms. I have a friend who works in eBay, and he says that they classify the images using k-nearest neighbors just to check if the image corresponds to the content of the um, of the, uh, of the things that they sell. So, but the problem with the algorithm is that it's very space consuming, and there are modifications that are using also time consuming when we do like sorting of distances, but there is modification which uses a probabilistic search algorithm, and it works also for large data. And yeah, the first line actually the main problem that with k-nearest neighbors because usually other models work better. So, and today we will start a new model which is called linear regression. So I will introduce first the problem that we will do problem solving and some code examples. Okay, so linear model, and so in statistics, it's typically called linear model because linear regression um, assumes the uh, known distribution of the features. So typically in statistics by linear regression, people mean the joint distribution when you have joint distribution and on X and on features and on targets. Now we will, so I will write in parentheses regression, but in machine learning, everybody calls this linear regression. Regression. Because, so what is the problem? We have some data points. So this is X, this is Y, and we have some points, and we want to make a prediction for every X, and then we fit a line, just fit a line that minimizes the distances from this point to this line. So if let's see, so for example, this is the point X1. This is the true value Y1. But we will predict our this point. But we will predict this point as the point on this line. So this will be Y hat. And I think you agree that if we take arbitrary point X star, the prediction that we will make with this line, Y star, will be actually a good approximation of our data. So we want to minimize the distances to fit this line. We want to minimize the distances between our given points and this line. And there are two ways. You can minimize the distance like this horizontal or vertical. You can minimize this distance. Or you can minimize this distance, the perpendicular. And in reality, it's the same because you can, if you know the slope of this line, then you can represent this hypotenuse with through these tangents. So our loss function, it's called the sum of squared residuals. The sum of squared residuals is the sum of differences between the true value y and the value on the line, which is y hat. Y hat squared. And we take the sum over all these errors, residuals. Okay, and now the model, how actually this y hat looks like. Y hat for point I, we will model with a linear function with some coefficient, which we call bias term, plus some coefficient that we multiply by the dependent variable x. So this is our model. If you substitute this model, this representation in our sum of squared residuals, you will get a function of two variables. So it will be a function of two variables of w0 and w1 that we call weights. That's why we use w. Of course, you can use a plus ax plus b and so on, but we will use w because we will reference to these numbers as weights of our model. Okay, so do we want to maximize or minimize the error? Minimize. Yeah, so then we want to minimize to minim. And we will minimize with respect to these parameters w0 and w1. So this is the optimization problem. And actually, the process of finding the solution is called training or learning. That's why it's called machine learning. We learn the parameters from data, from x and y. So, do you know how? So the first, first question. How does this function look like? So this is a function of two variables.
Provide Euclidean standard deviation.
No, I mean, what is the shape of this function?
You curve.
Yes, it's curve. Which curve? Which curve? There are many curves. What is the highest power? Yes, you can just choose.
Reminds me of quadratic.
Yes, it's quadratic function or paraboloid. So, do you know how to minimize functions? So let's just, I will do a quick review. So if you have a function like quadratic function, you can calculate the normal vector is perpendicular to the tangent line. And if you look at the projection of this vector, it's called the derivative, or in multidimensional case, we will call this gradient. So what will be the projection at the minimum point? What will be the length of this projection at minimum point? The vector will point down and projection will be zero. So the classical way to solve it, take the derivative, because this is the projection actually is derivative and equate to 0. So it's in one-dimensional case. In two-dimensional case, we will make a section of our curve, instead of our curve of our paraboloid. And when we fix one coordinate, for example, x, then we will have a function of one variable. And we will take, again, derivative only with respect to, in this case, y. Then we will fix another, and the notation is this one. So instead of t, we use partial derivative because now we have function of two variables. And d represents a differential, and differential in two-dimensional case is the sum of partial derivatives. So that's why we use a different notation. And so we take the section with respect to another axis, calculate the derivative with respect to x. Then we just take the sum of these vectors. And you know, remember the sum is just using this parallelogram rule. So this will be the sum of these vectors, and this will be the normal vector to our surface at this point. And the projection on plane is called gradient. And again, at the minimum, this projection should be 0. Okay, now we're ready to the problem solving, and we have our class assistant today, Matt, will help you to conduct the problem solving.
Have the Zoom link? I couldn't find it on
Yeah, it's on my courses.
I might have missed it.
Um, oh,
I just have no data when I try and join.
but if you have USB-C, you can actually connect directly.
I should be able to.
But okay, so
Yeah.
no, it's not here. So just
Yeah.
on my courses and under.
Oh, I didn't realize you had a separate one. Okay, great. Does this have USB-C?
Yes.
Okay,
If
great.
you need. Do you need?
Yeah.
Recording in progress.
Oh, it's and I don't should just
You have to move yourself.
down.
I don't know if it does.
No.
Oh, I see. Okay. Look at that. All right. I think that's
Is it?
I think they sorry about that, guys.
The microphone that I didn't use.
Okay, great. Cool. Let me pull this up. So yeah, I'm Matt London. I'm your course grader. Hopefully you guys don't all completely hate me from being too harsh on your last problem set, but here I'm going to show you how to do the problem solving. So let me just go to that, share my screen on Zoom. You have to make me like a co-host so I can share my screen. Oh yeah. Does anybody else need one of the papers? There you go. rest here if anybody wants another one at the end. Great, let me try that. Okay, cool. So you all should have this on your handout. We have 3 points, and we're going to use the sum of squared errors like we saw earlier to minimize the function and try and find our line of best fit. If you've seen this in another class like statistics, just like the professor was showing, you're trying to fit a potentially not perfectly straight line of data. So we're going to be using the partial derivatives for that. Has everybody seen partial derivatives? If not, they're just like normal derivatives, but when you're differentiating with respect to a variable, if there's other variables that you have to differentiate, you treat them like a constant. So we'll go through this for the first step, and if you have any questions, feel free to stop me and I can go further into it. All right, so this is our loss function here. So we're trying to get our loss as small as possible. So the first thing we're going to do is differentiate with respect to W0. So here, it's just like using the chain rule, as I'm sure you guys have seen before. So it's 2 times y1 minus, my handwriting is also not great. So if you can't read that, stop me and I can try and rewrite a little bit clearer. And then we do the derivative inside, which is 0 for y1. And then we are differentiating with respect to W0. So this is -1. And then here we're treating this as a constant. So that's 0 as well. So it's just -1. And then we move on over here. And we have 2. This is 0. First we got to put everything inside of the parentheses. And then differentiate the inside. So that's 0, and then -1, and then 0 again. And then the same for the third set. You get a little bit tight. y3. And then -1 again. Any questions on that? Everybody understands how I got that? Great. All right. And then we're going to do the same thing, but we're going to differentiate with respect to W1. All right. And then this is a constant, so that's 0. We're treating this as a constant, so that's 0. And then this is what we're differentiating with respect to, so that is not 0. So we multiply by negative W1, or wait, excuse me, negative X1. And then to the next set of parentheses. And then same thing here, we have negative X2. And then to the next set, I'm going to go on to the next line. And then negative X3. All right, everybody's clear on that? Awesome. So then we want to factor out W0 and W1. So we can look in here, and in this equation, we have minus W0. Actually, I'm going to rewrite these a little bit underneath to make it a little bit clearer. All right, so now that one I just moved the -1 around, so it makes a little bit more sense here. And then we're going to factor out. So if you look in here, we have W0 minus W1 X something in every single one. So we cannot factor out, we can pull out W0 from everyone. Hold on, I have to think about this. Let me cheat a little bit. Oh, we have to expand first.
Underscore. You can just underscore W0 at every.
Okay.
Without expanding, just underline.
What do you mean? Without expanding?
W0 at every.
I was just going to expand and rewrite. It will take a second, but it might make it a little bit more clear. Okay. So we'll do that. -2y1 plus 2w0 plus 2w1 x1 minus 2y2 plus 2w0 plus 2w1 x2 minus 2y3 plus 2w0 plus 2w1 x3. Okay. So now we'll have that on one side. So we'll do plus 2w0. And that's 6w0. And then we have plus 2w1 x1 plus 2w1 x2 plus 2w1 x3. Now we have all of these, and then it's minus 2y1 minus 2y2 and minus 2y3. Okay. So then we can factor out w2w1 from everything, and that can become 6w0 plus 2w1 x1 plus x2 plus x3 minus 2y1. Yeah, I won't bother factoring out the -2. All right, and then we can equate that to 0. We actually will factor out the -2. Just kidding. That'll make it easier in the next step. Okay. So then we have to do this partial derivative. So I'm going to do the same thing. So this is 2y1 minus 2w0 minus 2. Oh, we have, I'm sorry. Yeah. Say it again? Yeah, yeah. -2 x1 y1, -2 x1 w0. That's actually positive. +2 x1 w1 x1. I'll take care of all the weirdness afterwards. -2 x2 y2 plus 2 x2 w0 plus 2 x2 w1 x2. Sorry, it's getting really sloppy. Minus 2 x3 plus 2 w0 x3 plus 2 w1 x3 x3. All right, and then that should make it a little bit easier to factor everything. So if you look here, we have a couple different terms. We have x1 times y1. We also have x2 times y2 and x3 times y3, which is Looks like I wrote it wrong. This is supposed to be y3. So you can see there's kind of a pattern. We also have x1 times w0, x1 times w1, and then we'll have x2 times w0 and x2 times w1. So I'm going to group all of those together, and that'll make it a little bit easier to factor everything. So we'll have -2 times x1 y1 plus x2 y2 plus x3 y3. And then our other kind of term was w0 multiplied by each value of x, or 2w0. So plus 2 w0 x1 plus x2 plus x3. So then we have this, that, and we have this one, and this one. And then we have one more kind of term left, and that's 2w1 times the square of each of our x coordinates. So I'm going to add that. Let me slide all this over. And that is plus 2 w1 x1 squared. I'm going to use parentheses so it's a little bit clearer. Squared plus x2 squared plus x3 squared. All right, everybody understands how we got to that point? No? Okay. How we got to the squares? You mean here? All right, good question. So if you look in here, I wrote it kind of weirdly, but we ended up with another kind of factor, which was 2x1 times w1 times x1. So we just turned that into 2w1 x1 squared. Does that part make sense? And then you can see that term exists for every kind of x coordinate. So we have it there, and we also have it for x3. Does that make sense? Any other questions? Cool. Okay. So we're setting that to 0, and I think that's the simplest we can get it for now. Yep. And then the next step will make it a little bit more clear as well. So we divide everything by 6 and then rewrite it in this way. If you've done statistics, you've probably seen x bar, so it's the mean of x. So that's exactly what it is. Same with y. An important distinction here is this is x squared before we take the mean. So that's a mistake I made when I was solving this problem set, is I just took this and squared it, but those are two different things. I'll use parentheses to try and make that clear, but yeah, so we're going to substitute all of these in, and that'll simplify our equation even further. I will copy this up top so it's easier to write from. See how well that fits. All right, that's just temporary. I'm going to erase that. All right, so if we substitute in x after dividing by 3, so here we would be left with, or dividing by 6, w0 plus w1 over 3 times x1 plus x2 plus x3. So that's the same as x bar that we just looked at. And then we'd have minus 2, or rather 1 over 3 times y1, etc., which is the same as y bar. So we're going to rewrite that as w0 plus w1 x bar minus y bar equals 0. Any questions on how we got to that? Great. Next one is a little bit more complicated. So we're going to do the same thing. We're going to divide by 6. And for our first term, we're going to be left with (-1/3 times x1, y1 plus x2, y2, etc. So that's the same as down here. We had x times y bar. So we're going to rewrite that negative xy bar. And then for our next term, we had plus 2 w0 times all of our x's, and we're dividing by 6. So that's going to be plus w0 and then x bar. And then similarly here, this is the distinction I made where it's x squared bar, not x bar squared. And once we divide by 6, we're going to be left with w1 x squared bar equals 0. Yeah. Yes? Question? Okay, great. Any questions on how we got to this point? All right, so our equation's a little bit more clear now, so it's going to be a lot easier to solve. And yeah, we can just start solving. So for W0 and W1, you just solve it like a system. So I'm going to solve equation 1 first for W0, and we have W0 equals y bar minus W1 x bar, and then I'm going to substitute that into equation 2. Hopefully you guys are pretty familiar with this. All right, and then we can solve this. It's important to not combine these terms as xy bar because that's something else. So just be very careful when you're expanding and factoring that you're not making that that mistake. Same here. This is x bar squared. This is not x squared bar. And then here we're solving for W1. So let's get that to one side. W1 x squared bar minus W1. All right, factor out W1. I'm going to stop writing that. I'm just going to write a dot so it's clear that it's separated. All right, and that's our value for W1. Any questions on how we got that? Great. I'm just going to write that in here. And then we're going to substitute that in for our value of W0. I should have enough space for this. So we're going to take this equation for that. W0 equals y bar minus. I'm actually going to move some stuff. X bar. All right. Y bar minus, and then we can multiply this in. Yeah. Would it make more sense to leave it like that? Just making sure we shouldn't separate it in the final one. Yeah, that does simplify quite a bit. That's not right.
Just multiply the first term by the denominator.
Oh, I'm sorry. Yeah, I see. Y1. Yeah, or Y bar. Whoops. Thank you.
Just simplify it.
All right. Now we can expand this, and hopefully you can see now why it was important to have the parentheses, not mix up your x squared bar and x bar squared. So then we have x squared y bar minus x bar squared. All right, and then we have these terms can be simplified. Undo those so it's not in my way. We should be able to go further than that, right? Am I missing something? Did I miss a negative? It's y0, the whole, oh, I see. This whole thing is negative, and I dropped that at some point. Sorry about that, guys. Okay. So we'll just retroactively fit that in. And I'm just going to rewrite the numerator to make that more clear. So this will end up as x.
Sorry. On the previous line, you corrected the wrong lines. Should be negative instead of plus, and the last minus should be plus.
Oh, I missed one. Yep. Thank you.
I mean, you don't mean that you corrected the wrong plus. The previous will be minus.
So this was
the first one was positive in the fraction.
right.
Now it will be negative.
All right. Let me rewrite the numerator on that.
No, you don't think that's very one plus. Like.
Yeah, but when I was expanding, I did something kind of weird.
Well, let's see. So these should be positive. This should be a negative, and this should be positive.
Okay. Okay. How does that look? Someone say wrong? What part?
The plus should be minus. And the
Oh boy. All right. All right.
let's see. Let's see if we will get some stuff, something cancel out. Yeah, actually we will get cancel out y bar times x.
Right. Yep, that looks better. Okay. X squared y bar minus x bar xy bar. And then that's over that. Even that should simplify further. No, but I think it's just a different
Yeah,
form.
you can simplify further, but it will be like kind of
Yeah.
calculation of derivation.
Yeah. I'll just leave it. All right, great.
Well, actually, for our purpose, it was we could stop actually here because when you calculate this W1, you will just substitute this number here.
Oh, right.
Okay,
Right. Oh, sorry about that. All right. So that was a lot more work than it was supposed to be. I apologize for that. Let's actually just write in here y bar minus W1, and then I think it should be X bar. Yeah. So we're just writing exactly this. Yeah. Whoops. All right. Sorry about that. Cool. Okay. So now it comes to calculating the weights and plotting the line. Does anybody need any of this stuff? Because I'm gonna erase some of it that's in the way. Yes.
Wait, are we talking about the left half of the page or the right half? Because I need
The left half of the page. I just want to erase all this that's over the graph.
It's fine, but you need a bit more time to talk about the right side.
Okay. I'll just move it.
Oh,
So what happened was I substituted in our value for W1 here. I'll go to like a pointer. I substituted in the value we had for W1 into this equation.
and then we don't need to do any other
That just wasn't necessary, so we went all the way back. It was just a test, making sure everybody's on their toes. I wasn't, so got all the way here. Does that answer your question? All right, great. Yeah. Why do we divide by 6? Because then we can end up taking the average. So if you look at, you're familiar with these equations, right? If you're not, it's fine. I can explain it. So it's basically the average of x's, the average of y's, the average of x units squared. Does that make sense? So then when we divide by 6, our benefit is that, for example, this term, when we divide that by 6, we get W1 over 3, like we had here, and then X1 plus X2 plus X3. And so since that's literally just W1 times the average of X's, it just makes our equation a lot simpler. That was given to you, so you don't have to worry about how that was derived. But that's the reason we did that, so that we have these somewhat simple equations compared with what we would have if we continuously brought through each individual x. Does that answer your question? Yeah. Great. Yeah. That's correct. Yep. Anything else? All right, we can start actually substituting in some numbers. So we're going to have to start with W1 because in order to solve for W0, we need the value of W1. So these are data points. We have 1, 1, 2, 3 over 2, 3, and 5 over 2. And so if you look at W1, we need XY bar, we need X bar, we need Y bar, and we need X squared bar. So we can just individually calculate those using the formulas that were given. So X bar, we'll start with that, is the average of X's. So that's 1 plus 2 is 3 plus 3 is 6 divided by 3 is 2, not 3, 2. And then the average of Y's, 1 plus 3 over 2 plus 5 over 2. So that's 8 over 2, which is 4, plus 1 is 5, divided by 3 is 5 over 3. Stop me if I make any mental math mistakes. And then multiplying that, we don't have to worry about that right now. And then x squared bar we have 1 squared is 1, plus 2 squared is 4, plus 3 squared is 9. That's 14 divided by 3. And then, is that all we need? No, we need xy bar. And the first one is 1 plus 2, 3 over 2, which is 3, plus 3, 5 over 2, which is 15 over 2, all divided by 3, that's 4, and then 8 over 2, that should be 23 over 2. I make a mistake, 23, 4. Because we had 4 plus, and that becomes 8 over 2, and I can add that to 15 over 2. Yeah. Yeah, no, I didn't just. Yeah, so then it should be 23 over 2, which is 23, whoops, over 6. That makes sense? Yeah.
You get x squared bar is 14 over 3 because like your x bar is 2, right? So if you square it, is it 4? Wait, that's actually like
That's a good question. Yep. So what's happening is x bar squared is different than x squared bar. Does that make sense, or do you want me to go through it again?
just like tell me like real quick how you got 14 over 3.
Yeah. So x squared bar is we have x and then we square everything and add it together. So 1 squared is 1, 2 squared is 4, 3 squared is 9. We add all that together, we get 14. Yep. So it's the average of each x squared added together. All right. So then we can start substituting those in. So we have xy, that's 20. I'm substituting into this equation, by the way. 23 over 6 minus x bar times y bar 2 times 5 over 3 divided by x squared bar 14 over 3 minus x bar squared, which is 4. And then we can start simplifying this, or I could just plug it into a calculator. Any preference? Okay. I don't have a calculator handy, so maybe I'll just go through it. 23 over 6 minus 10 over 3, which is 20 over 6. Whoops, 20 over 6. So that's 3 over 6 in the numerator. And then 14 over 3 minus 4, 12 over 3. That is correct. So 2 over 3. And then we can divide those. So that's 3 over 6 times 3 over 2, which is 9 over 12, or 3 over 4. So that's 3/4. Any questions on how we got to that? It's a little messy, but it's just substituting in. So that's our value for W1. And then W0 is a lot easier because we left it in terms of W1. So it's just Y bar. And I'm going to do it right over here. It's Y bar, which we calculated as 5 over 3. Whoops. Minus W1, which we just calculated as 3/4. And then X bar, which is 2. And that becomes 5 over 3 minus 3 over 2, which then becomes 10 over 6 and 9 over 6, which is 1/6. So our W0 is 1 over 6. And we can graph that down here, just like you would if it was like y equals mx plus b, or however you learned it. So first, sorry? Yeah, okay. So that's y equals 1 over 6 plus 3 over 4 times x. So that's our final equation. And then you can plot it down below. I can do that quickly. 1 over 6 is, I should know that. What is that? 0.16? Yeah, half of that. Go like there. And then we get 3/4. So we'll go up 3, 1, 2. 3/4. So yeah, up 3/4, just like you learned in 7th grade. Cool. And then we can plot that. Yeah, you see? Did I count wrong? 1, 2, 3, 4. 1, 2, 3. Looks right. Yeah. In this point, x would equal 1. Oh yeah. Yeah, this would be equal to 2. Yeah. Yeah, you're right. Yeah. That's okay. Plot this. Let's get like kind of a straight line and move that down. So yeah, that's our line of best fit. You can see how we should end up with minimized error with each of these points. Any questions? Awesome.
Because last year I gave this software class without any hints, and you can imagine how hard it was to figure out that this W1, W0. So I think that's
Yep.
some important for sure.
Glad to hear it. Happy to help out. I'll leave.
So I think I have in this problem with sharing screen. So this formulas actually work for arbitrary number of points. That's why we use bars. Just you can use them for arbitrary n. But we won't use them next time. I thought we will have time tomorrow today. Next time we will derive the closed form solution using matrix notations, and it will be just one very simple equation. So for today, let's see. Maybe we can just represent loss function with closed form solution. So what I want to clarify now, the difference between loss function and SSR, because if we use loss function, which is called MSE loss of W0 and W1. Oh, I'm not, wait a second, it's not projecting. like we have the same problem again. Um, I'm sorry, I just want to make one final remark, and projector didn't work. I believe. I believe I can solve this with also going into settings of the screen. Doesn't anybody remember what are these settings of the screen? Is it? Oh, maybe it's display. Let's see. And display. Yeah, yeah, yeah. Sure. I believe it's in display in this place. Oh, this thing.
It's probably like on this thing. Oh, connected to. You want to plug in the? Do you have a USB-C port?
No, it should be HDMI.
Oh, fine. Sorry. Finding that again. Computer.
Yeah. I don't think
Oh, try this.
it will work. Let's see. Oh, it looks like it's working.
So,
Yeah,
There we
it's
go.
working. So, okay. Thank you, Cedric. So, okay, final remark. What's the difference between SSR and loss function? The difference is that loss function is divided by the number of points. So, and we call this MSE loss, MSE loss. So what is the point for taking the average of our error? Well, the first, like, straightforward idea is that we want to estimate the error for one point, because here is the sum of errors over all points, and here we estimate the error for one point. But there is a deeper idea when we want to minimize. So I didn't have time on the first lecture to talk about this, so I will explain it now. So when we have loss function, when we have our model, then one argument will depend on x. And if we want and we don't know the distribution of our data. If we don't know distribution, we can take the average or expected value. But when we take expected value, there is the probability of our distribution, which we don't know. So this is called expected loss. When we don't know probability, we substitute this with uniform distribution 1 over m. And then it's called empirical loss. And in machine learning, we work with empirical loss. So that's why we calculate the difference, the square difference for one point, the sum over all points, and 1 over n is actually the unknown probability that we just substitute into this probability 1 over n. And in machine learning, and in statistics, we try to minimize not just loss, but it's called empirical loss. But we just use the word loss function. Okay, so that's it for today. And yeah, have a great day. Yeah, you can leave on the desks your papers. And Alina, you can send me by email the problem solving. Okay, yeah. Have a good day.